Welcome to the second lecture, that is dynamic equation of motion of a two-link manipulator using Lagrange-Euler approach. So in this lecture, I'll continue with two-link manipulator or an arm using Lagrange-Euler approach. We'll obtain dynamic equation of motion for this. We'll interpret dynamic equation of motion various terms which are there at the end. Okay. So let us continue with two-link manipulator. It is defined here as, it is just a massless link, that is link 1 ends with the bob of mass m1 and it is attached with a joint here and there is a second link of mass 0 ends with the mass m2, that is a bob here, m2 concentrated mass. So both m1 and m2 are concentrated mass, whereas the links are of 0 mass. Okay. Theta 1 and theta 2 are the relative joint angles. So this is theta 1 and relative joint angle theta 2 is here. Okay. It is suspended from the top where you have the reference frame, x is directed along positive x axis, y like this. Okay. This is your reference frame 0. So this is how it is defined. So now let us continue using Lagrange-Euler approach. The first thing that we'll do, we'll try to find out the kinetic energy and potential energy for both, that is for joint 1, that is for mass 1 and similarly for mass 2, we'll obtain that. Okay. So kinetic energy 1 as we have done earlier for the one link manipulator. So we'll do it exactly in the same way. We can directly obtain using 1 by 2 m1 x dot square and y1 dot square. So that should give me 1 by 2 m1 v square, or alternately 1 by 2 m l1 square, that is I, and similarly theta dot square, that is omega square, theta 1 dot square. So this should be there. So using that I obtained my kinetic energy for the bob 1. Now moving to the kinetic energy for the bob 2, this is for m2. So again I have obtained x2 and y2 first as we did it earlier. So this is my x2 is equal to this plus this, got it. So it is equal to L1 sin theta 1 plus L2 sin theta 1 plus theta 2, and similarly you can obtain L1 cos theta 1 and L2 cos theta 1 plus theta 2, right. Summing them together you can directly get the displacements along y and along x. Mind it, this displacement along y is considered negative because it is below this point, that is the reference point. Okay. So these are x and y, okay, that can directly be obtained using projections as we have done. So taking derivative of this, I get the velocity along x, x2 dot and y2 dot, got it. So I have obtained this, and squaring and summing would give me the resultant velocity v2 due to x2 dot and y2 dot, and that is squaring and adding I can directly get this. So v2 becomes equal to this, and I have just eliminated the terms sin square theta plus cos square theta is equal to 1 from this. This can be reduced to this, and I have also used cos A cos B plus sin A sin B, as you know is a trigonometrical identity. Using that you can reduce it to this. So these are few identities which are used here to reduce it, and I got the v2. Okay, that is the velocity for the bob 2. For kinetic energy, this is equal to 1 by 2 m v2 square. So you can directly use this term here, 1 by 2 m2 v2 square. That gives me this kinetic energy, got it. So kinetic energy for the first bob and the second bob both are obtained. Now I will sum them together to get the total kinetic energy of the system. You know, for Lagrangian you need total kinetic energy. Okay. Now the potential energy. Potential energy is very straightforward. It is mg into L1C1. Let us go back to this and you can just see here it is L1C1. So this is the mass, this is acceleration due to gravity. Got it? So it is directly m1g L1C1. So this is your potential energy for the first bob, and similarly for the second bob, both of them I have added here and I got the total potential energy. Got it? For the second one you have used what? You have used total distance here, that is L2C12. So it is L1C1 plus L2C12 M2 into minus G. So all those will come here and finally it will make it to this. Okay, so this is the potential energy for the second bob, and both summing together I got it this. Okay, so this is total potential energy P1 plus P2, which is here. Okay, so now I'll use K and P, total potential and total kinetic energies, and I'll obtain what? Lagrangian. This is the Lagrangian of the system. Kinetic energy minus potential energy, K minus P. Okay. So now I'll use this, that is the Lagrange-Euler formulation. It is defined as tau here because it is both of the joints are revolute joints. So it will be tau, and joint angle will be joint angular displacement. So that is theta 1 dot and theta 1. Similarly for the second one it will be theta 2 dot and theta 2 here. Okay, and tau 1 and tau 2 are the joint torques. That should be the case. So independently for both the joints we will have to use this one. Okay, so starting with again the first bracketed term which is here, that you can see. So if this is the Lagrangian, okay, for the first joint variable dou L by dou theta 1 dot, I have discarded all the terms which doesn't have theta 1 dot, and the whole of this gets reduced. So this term goes off, this term goes off, even this will go off. Okay, only the terms which has theta 1 dot will remain, and taking partial derivative I get to this. Now with time derivative this becomes this. So again all the terms which has theta 1 dot will go to theta 1 double dot. Taking common it leads to this. Okay. So this is the first term of the Lagrange-Euler expression. The second term can be derived as dou L by dou theta 1. So in this case all the terms which doesn't have pure theta 1 can go off. Okay. So this will go, this will go, this will go, only the term which is here would remain, and taking partial derivative with theta 1 gives me this. Okay. So now summing these two terms together and forming my Lagrange-Euler equation, it leads to this. So tau 1 is equal to d by dt dou L by dou theta 1 dot minus dou L by dou theta 1. Okay. So that gives me tau 1. So that is whole of this and this together. Okay. So that is clubbed together like this. Similarly for the second joint I will use the same Lagrangian here, that is the system Lagrangian. Take partial derivative with respect to theta 2 dot. Again this time I will neglect all the terms that has theta 1 dot. Okay. So all the terms which has theta 1 dot will go away. Okay. So only few terms are remaining. Okay. So it will lead to this. Now time derivative of this would be this. So it is dou L by dou theta 2 dot d by dt. So all the theta 2 dot terms and theta 1 dot terms would become double dots. Okay. So it leads to this. So now taking dou L by dou theta 2, that is the second term of the Lagrangian. This time it is theta 2. So all the terms that has theta 2 only will remain. So it is this term and this term only. Remaining all of them, they don't have theta 2 alone. Okay. So either they have theta 1 dot, theta 2 dot or theta 1. So all those will be ignored. So dou L by dou theta 2 would become derivatives of this, okay, this and this. So both the terms of the Lagrange-Euler expression is obtained. From there I can obtain the equation of motion, okay, for the second joint, okay. So from equation 1 again I can take the sum of both of these and I can write tau 2 is equal to sum of this and this. So it gives me tau 2. Now packing both the equations together, both are scalar expression. Now can I write it in vector matrix form? So it can be packed like this. You see tau 1 and tau 2 can be written like this. All the terms which has theta 1 double dot and theta 2 double dot is expressed in a matrix form, matrix vector form. So this is your column vector for acceleration, okay, and you are remaining with the terms, this one, okay, and this one, okay, for this, okay. All the terms that has this will only remain. In this case, in the second one you have this and this. So those terms will appear here. So this is a 2 cross 2 matrix, and now the second term, it has theta 1 dot square and theta 2 dot square. Those can be packed together. All the terms which has got the square of joint angle rates comes here. Again you will get a 2 cross 2 matrix which is here. The third term has got product of matrices, that is theta 1 dot and theta 2 dot, okay. Those are considered here, and again you will get 2 cross 2 matrix, and the terms which are left over last, like these, all the terms can be packed over here. They have g with us, okay. Acceleration due to gravity terms will come like this. So it contains 4 terms. The first term will have joint accelerations, the second term will have joint velocity square, the third term will have product of joint velocities, and term doesn't depend on joint velocities, okay. It only depends on joint angles, okay. So now this is the general equation of motion for any robot, okay. It can be expressed like this. So first term you saw tau 1 and tau 2, that is arising out of equivalent inertia component. So this is equivalent to moment of inertia of the system at any instant of time and inertia into acceleration. So these are the accelerations, okay. The second term is centripetal component. As you see, it is I omega square, it has dimension of that only, that has omega square terms which are here, and the third term is Coriolis component. So that has theta 1 dot into theta 2 dot. So those terms are here, that is product of angular velocities term, and the final one is the gravity component which depends on g, and they do not depend on theta 1 dot or theta 1 double dot. Similarly theta 2 dot or theta 2 double dot, joint velocity and acceleration, they don't, it doesn't depend on that. So this is there even when the robot is static, okay. So this is written as this, tau is equal to I theta double dot h theta 1 dot square, theta 2 dot square, c is the function of theta 1 dot and theta 2 dot, and gamma theta 1 theta 2, right. So this is the general equation of motion for any robot, okay. So in this case all these matrices are 2 cross 2, okay. In case of any general robot of n degree of freedom, it will be n cross n, okay. So now let me further express it physically, okay. So these are some interpretation of dynamic equation of motion as you have seen, okay. The first term is the equivalent component moment of inertia, okay. So let us say this robot at any instant of time is this, okay, it is like this, okay. for joint 1, so let us assume this is rigid, the joint is fixed over here. So this is the practically the shape of this link. Okay. So equivalent moment of inertia in this posture would cause torque at this joint, is it not? So while considering the torque at joint 1, link is considered like this. Okay. But when considering the moment of inertia at joint 2, okay, over here the link is like this and motion is because of the first joint motion and the second joint motion, both of them will appear here and that will cause torque over here. Okay. So the shape here is very simple, it is straight, but in case of the first joint it is like this. Okay. So this is varying moment of inertia. With time the shape of the link changes. Okay. The configuration of the link changes. With time variation is there in configuration of the system. Okay. The whole of the moment of inertia keeps varying all the time. Okay. So now the second term, it is the centripetal term. Again, due to the change in shape, the moment, the centrifugal force because of the first CG is outward. It is very simple. Okay. Centrifugal force is outward, centripetal force is inwards, that is okay. But in the second link, due to the configuration of this joint, this direction keeps on changing. Okay. This link configuration keeps on changing. Accordingly, this will change. Okay. So this mass will create centrifugal force outward like this, and centripetal force will now create torque over here. Okay. So these are few intrinsics of this, you should understand this element wise. Okay. That is the physical significance of each of these terms. Okay. So again the Coriolis term, that is the second last term, you see in this case this link is very simple and it just have angular velocity here and mass is here. Okay. Whereas in second joint this causes motion to the second link. In this case it has both, it is both rotating and it is translating. Okay. So this definitely will have Coriolis component as well. Okay. It is not a pure rotation. Okay. So the center of mass is rotating as well as translating along the axes. Okay. So resultant velocity, resultant motion will create Coriolis component. Okay. The last component, that is acceleration due to gravity, it is not because of motion, it is because robot has to stay there and gravitational forces are creating this component. Okay. So yes, all these comprise of final equation of, all these are components of equation of motion. This all forms the equation of motion. Okay. So that's all for this lecture. In this lecture we derived the equation of motion of a two-link manipulator. Okay. And we have interpreted that. So in the next lecture we will continue further with robot dynamics. We will learn what is Newton-Euler approach to derive equation of motion. We will also extend it further to recursive Newton-Euler approach. Okay. That's all. Thanks a lot.